Hi, everybody. Welcome to Sound Design for Oculus Quest and Beyond. I'm Tom Smurdon. I'm the audio content lead. This is Pete Stirling. He's the audio engineering lead. Oh. Thanks. So a few things we're going to go over today is performance of the Oculus Quest. How many sounds can we get out of it? How many voices? And that's all spatialized voices. We're going to go over BONGO, which was experience we came up with up in Seattle with the Oculus Rex team, and that was just a test to see how far we can push the Quest. And so we're going to talk about the audio part of that. Pete's going to dive into dynamic room modeling, and he's also going to be talking about the work that Facebook Reality Labs has been doing with Propagation. And then we're going to dive into what the Oculus Audio SDK is going to have coming up soon. A lot of people have been talking about 3DOF versus 6DOF. I'm just going to explain that really quick again. So 3DOF is what the Oculus Go and Gear have. That's 3 degrees of freedom. That's just when your head can pivot left and right, and everything's on a pivot. So sound designing for that is a little different than working with 6DOF. 6DOF is more what working on Rift is like, where people will actually move around. Like in BONGO, we found people would like get on the ground next to different things, and since it's untethered, people tend to move around a lot, and so you have to watch all your attenuation curves and everything else. I'll go into more of that later, but next Pete's gonna talk about performance.
Yeah, so like Tom was saying, with Oculus Quest, it's a 6 degree of freedom headset, and this is more like Rift. And so people are going to be expecting very high fidelity experiences. But achieving a high fidelity experience on a mobile headset is a challenge, and so you need to be aware of some of the performance considerations. So I'm going to be going through that with you now. So when we talk about performance, there's a few different elements here that you need to think about. Now, the biggest difference between a PC and a mobile chipset is the GPU. It functions very differently, and this is where the vast majority of resources, programming and engineering time will go into porting a title from Rift to Oculus Quest. Fortunately for us, we don't worry about the graphics, but the CPU is very important for audio because that's where all our signal processing, the spatializer, everything's running on the CPU. So this is going to be the biggest priority for audio people like your good selves. Memory budget is another thing to be mindful of. Again, it's going to be less than what you've got on PC. On PC, you could have 16, 32 gigs, sort of the sky's the limit. On a mobile platform, it's more constrained. You're going to be more in the ballpark of 2 gigabytes. And you're sharing that with the rest of the game, all of the textures and the geometry and the other things going on. So you might want to be thinking about more compression and that sort of stuff, and having a more constrained amount of memory being used. And another thing to think of is the size on disk. So on PC, you might have a 3 terabyte hard disk. You can install thousands of games. On these devices, on Oculus Quest, you're going to have much less space. And so having a smaller app size is going to be important, which again is going to affect the size of the assets and the type of compression you're using on your audio. So something I think is really good to do at the outset when you're working on a constrained platform is to have some idea of what these performance constraints are going to be ahead of time. So work with the engineers on your team and talk about what sort of CPU budget you can have for audio and the performance budgets for memory and disk space and those sorts of things as well. And if you know those ahead of time, it can help you plan out the project and think a little bit about how to maximize the performance you can get out of the device. Now, I've got some numbers here, and these are kind of ballpark numbers. I ran some performance tests on an Oculus Quest, and this will give you an idea of what the performance cost is of some of the major features of the audio spatializer. So the direct path HRTF from the source to the listener is about 0.4%. So this is really cheap. And you can definitely afford to put this on every single sound, and we highly encourage that you do that. It's really important to spatialize all the audio in the scene so you're getting that real spatial image of the sound. And at this performance cost, there's no reason not to. Now, the more advanced features like early reflections, these are a little bit more expensive performance-wise. So it's almost 10 times as much. And so you don't want to be having early reflections on everything. That's going to absolutely kill the CPU. So you want to be really mindful of using that if you use it at all. Generally, for Oculus Go and Gear VR, we recommend people just turn reflections off. It's kind of an easy way to keep the CPU budget under control. But if you've got some good reasons or you've got some feature sounds, you may want to use it on one or two. That would be totally fine. And the other piece here is the reverb. And you can see that's sort of similar cost to the early reflections. But this is a shared performance cost because there's one instance of the reverb and all instances are sending to it. So if you're using our reverb, you only pay that fixed cost. So it's totally reasonable to be using the reverb and the direct path HRTF. There's obviously other options for reverb. Middleware provides reverb solutions. There's other plugins as well. They're all viable options. But if you're evaluating a new reverb for your next title, I highly recommend you include ours in the list. We rewrote it last year, and it sounds quite good, and it's really fast. So it's definitely worth trying that out. And so that's kind of the theory behind it. But I'm going to hand back to Tom to talk about an actual project.
Actual project.
A real one.
So BONGO was the experience we made up in Seattle with the Oculus Rex team. That's also known as the Oculus Real-Time Experience team. We made Dream Deck, and we made First Contact, and just a bunch of different things that everybody here, I'm sure, has seen already. So BONGO was just pushing the boundaries on Oculus Quest, what we could do. We went through a ton of iterations. It's a virtual pet. She's super cute, and she'll do all kinds of things, like she'll fetch sticks. She gets dirty in some mud, you can clean her up, you can feed her, all kinds of different things. Watch a fireworks show with her. Here's a little clip so you can check it out. So there's BONGO. Yeah, thanks. So we didn't use any early reflections at all. And as we're going through, we were seeing how many voices I could spatialize. I told the engineer what I was going to do, and I was like, just give me any feedback of anything, if I'm pushing any limits on anything. Never heard a peep out of them. So we got up to 64 spatialized voices. That's the limit of the spatializer anyway. So we used everything. We had multiple first-order ambisonic loops for music, ambiances, bugs, weather, and then there was a ton of animations for BONGO to make her feel realistic. And once again, since this is a 6-DoF headset that's untethered and people are wandering all over the place, you have to make sure like you create sounds like you would on the Rift, where you make sure all the sounds are coming from the right locations, like all the vocalizations are coming from the mouth, footsteps are coming from the feet, because you don't know where that listener is going to be listening from. Now, Pete was talking also about early reflections. We didn't use any on BONGO because the player, it wasn't that kind of game. But if you were on a game, let's say, where there's a robot and a train and they're in danger to the player, I would put early reflections on those two things. Just because you need to know where your enemies are, where sounds are coming from. The early reflections make the spatialization work better. And it's super important, like, for these two things. But everything else, it's all going to spatialize pretty well, but that just helps it out a little bit more. So just things that are important to the player, put early reflections on. We did use a shared reverb on everything on BONGO. It was a fixed cost. It wasn't a big deal. I also threw, I think, a compressor and limiter on the main bus. It's all on the CPU, so never heard any complaints from anybody, and everything ran really well. So, mixing for the Quest, it has those built-in speakers. I don't know if anybody was in the Carmack talk, but he was talking about the number of people in the Gear who were not using headphones, and it was the majority of people not using headphones. That means people putting in the Gear had their phone slapped on their face, and whatever speaker was on that phone, the sound was just blasting out. That was a really bad audio experience. When they came up with the Oculus Go headset, and they showed us the speakers. At first, Pete and I were leery. We're just like, oh, there's speakers. I don't know how this is going to sound. But once we got the headset on and tried it out, it sounded really good. We were super happy with it. It had good stereo separation because your head's actually blocking the speakers from each side, and things spatialize pretty well in it. Now on the Quest, we do have bigger drivers, so there's a little more low end. There still is not a lot of low end, so if you're going for that audiophile experience, there is 2 headphone ports, one on either side. You can use either one of them, and I think one of the jokes internally was like, if you want to have a friend who wants to listen to what you're doing at the same time, they can plug into the other one. I don't know how good that is, but it's a thing that's there. Also, it's hard to put on headphones while you're blindfolded, so the speakers actually work really well. We're super happy with them. When creating sounds, I use Nuendo, whatever DAW you use is fantastic, and then I'll make my sounds, and then I'll kind of build a project with all the sounds that I'm putting into the game itself. And then I'll run our plugin, like I use the VST version of it, we have it for all systems. I'll run our plugin and put all the sounds to the plugin, and then I'll EQ a little more, try to get things to sound better. Now, there's a pin and notch in there, but that moves depending on the angle of the sound from where you're at. So you don't want to dial out that pin and notch because that'll ruin all your externalization. It'll also ruin like all the spatialization. So just kind of get that in there so you get an idea what the filter sounds like, EQ it, pull that VST plugin off because you don't want to bounce anything down with the VST plugin on, and then use those sounds to put into your middleware or into Unity or Unreal or whatever you're using. By the way, BONGO was made using Unreal and Wise. So we had all the sounds, everything sounds good. Watch for the notch, get a rough feel for the mix. And the thing is, it doesn't really translate well like speakers you're listening to. You have to mix in the monitor, in the Quest headset. So this is going back a little bit. I was talking to some people about this already. Do your build, get it on the headset, and get somebody to take notes. If you don't have somebody to take notes, just put your phone on record and talk into your phone. You want to be in the headset and doing the experience, and it has to be in the headset to get a good mix. I'll just keep saying that over and over again. When you walk up to something, you want to test your attenuation curve. So let's say BOGO's over there, and I'm walking up to BOGO. It's like, does that sound natural? When I get right next to BOGO, does it get too loud? Make sure to watch all of that. It's a different experience when you have this full freedom to walk around and listen to everything. The attenuation curves are super important. So here we've got Brandon and Andy. Andy's taking the notes. And Brandon would say stuff like, oh, BOGO's voice is too loud, like 3 dB. Those footsteps over here, turn them down 2 dB. Music is overpowering at this spot, like 4 dB. And we just throw all these notes together. You go back in, make your changes in your middleware, send it to the headset again, go through it again. Keep repeating this until you get a good mix. Also, there is a Guardian built in, but some experiences are going to have a smaller play space. BOGO had a small play space. So we needed some way to warn the player that you were leaving this play space. So there's loud parts and soft parts in the experience. We were thinking, well, if we put sounds on it, if we put a loud sound on, let's say during the fireworks part, that sound's going to be way too loud during the soft parts. And if we put a soft sound that fits over here, it's not going to hear it in the fireworks part. So we're just like, you know what we could do? We'll just try the absence of sound. We did a low-pass filter that ramps nice and smooth so it's not jarring to the player because you still want to keep everybody immersed. Just let them know that they're, about to step out of the play area. Here's a little clip of what we did. So that's me backing away from the player like this, and then walking forward again. And here's me just walking out of the space, and then walking back in. And then I'll play it again without me talking. So the good thing about that, it was a soft notification. It wasn't jolting or jarring in any way. Next, we're going to have Pete talk about dynamic room modeling.
Yeah, so dynamic room modeling is a new feature we developed last year, and we shipped it shortly after Oculus Connect 4. So we didn't get a chance to talk about it then, but I wanted to take a chance to talk about it now, because I think this is really valuable, and I think a lot of people will be interested in how this works. So dynamic room modeling is this feature where we use the existing system that we already have for early reflections and the late reverb. And we often refer to this as the shoebox model. So we have this rectangular prism that we use to model the reflections. And what we add with dynamic room modeling is we're actually resizing that shoebox in real time to match the game space. So whatever virtual environment you're in, we're fitting the shoebox to that environment. So it's resizing in real time. And this is really great because it matches the same performance profile of the early reflections and the reverb system that we already have and we know works well across all the platforms. But it gives you this extra ability to have the space match where you feel like you are. So when you're in an open space, it's louder, longer reverbs. When you're in a tight corridor, you're hearing that sound bounce back and forward. And now I've got a video of that now to show you. And you'll see as I get into this corridor, it gets much narrower. Now I'm going to walk into this bigger space.
And speaking of the king, here's the king of the guitar, Jimi Hendrix, Army Specialist Zach Johnson.
You can hear that reverb really open up as you get into that space. So this is a feature. It's available now. It's in the Audio SDK. It works with Unity. We've also got it available for UE4 as well. And it's going to draw this overlay in-engine so you can see what's happening in real time. And there's some parameters you can use to dial it in. So how many rays it's casting and how fast the smoothing is. And the performance of the actual raycasting and stuff like that is really minimal. And it just leverages the game engine's raycaster. So it's just shooting a handful of rays out from the listener position just to kind of work out where the walls are. And it also allows you to get near a wall. So as you get close to a wall, that wall's there with the audio modeling, and you're hearing a slapback reflection off that wall. So it's a really effective little trick that it's a minor feature performance-wise, but I think it can add a lot of bang for buck.
So that works in Quest too, right?
Yeah.
Yeah, okay.
It works on Oculus Quest as well. But again, you don't want to be using early reflections on everything, but it will work with the reverb. So the RT60 and the decay properties of the reverb will be matching if you've got this on your Oculus Quest title. But this is really just scratching the surface of a much more complex problem. And this is one that multiple people have started working on in different ways, and that is propagation. And I wanted to talk a little bit about our approach to this. This is something that Facebook Reality Labs have been working on for a while, and they've come up with something really special. So I want to talk a little bit about the process we went through and talk a little bit about the problem we're solving and how we see it. So the state of the art for reverb modeling in AAA games would typically be something like this, where you've got your environment with a few separate rooms, and then the sound designer would dial in reverb presets for each of those rooms. And then you would fade between those reverbs as you move through them. And maybe in a really sophisticated thing, you might have multiple reverbs feeding into each other to try and hear sound propagating from one room to the next. You might have a portal system and some visibility to handle occlusion and those kinds of problems. But there's a lot of work involved in doing this. There's a lot of engineering effort that's involved, and then the sound designers need to dial it in. They need to work together, and then you've got to step through and debug the whole thing. So we wanted to find a solution that is much simpler to implement and more physically accurate. So we wanted to just take the actual game geometry and then have some materials to describe the acoustic properties of the scene. So you're going to have material properties that are going to be describing, say, the scattering coefficients, the transmission coefficients, absorption of all the different objects in the scene, and then do some modeling of that in software to accurately propagate the audio through that scene. And so this combines a whole bunch of different problems that have been solved in different ways. So you've obviously got the direct path from the source to the listener, as we always have done. And you've got those early reflections. But instead of bouncing off the shoebox model, they'll now be bouncing off the actual game geometry. And you've got that reverb, but that reverb as well is going to be informed by the geometry. And the reverb itself is going to be directional as well. If you've got a cave over on your right side, you want the reverb from the sounds in that cave to be over on the right. You don't want that all around you. So there's going to be a lot of asymmetry and things like that with the way the actual physical audio model would work. Another separate problem is occlusion. So that would usually be some game engine side thing where you're doing some raycasting to see visibility of the object. But with this sort of a system, it should all be included. And it's also going to be affecting the early reflections. So even though the sound's not visible, you still want those early reflections to be bouncing around the object. And obviously the reverb will not get occluded by a small box in the middle of the room either. So there's a few different approaches to this kind of a problem, but the biggest challenge here is the computational complexity. So one way to overcome that is to pre-compute everything. So you can lay out a grid of points in the world and then compute the audio pressure at all of those points and also the relationship between the points, the visibility and all of those factors to work out how the sound would propagate through the space and then just sort of use the nearest one or interpolate. And there's a few drawbacks to going this direction. So one of the main ones is the large offline compute time. It's going to take a long time to bake out that data. And all of that data is going to take up a lot of memory. So you're going to have to load it all up and keep it resident in memory. So that's another drawback here. And I think one of the biggest ones, and this comes from the large compute time, but that makes it a really long iteration time. So when you're trying to dial it in and get it all that fine tuning, you don't want to wait half an hour, however long it takes to bake it all out, to hear it again. You're going to forget what you were listening for. You're not going to have a smooth workflow working that way. And then technical limitation here is its limit to static environments. So if you've got a door in the space and you've baked out the reverb with that door closed, in-game, when that door opens, the sound's not actually going to pass through that door. Or if it does, you're going to have work around some limitations of the pre-baking. So we wanted to find a better way to approach this. So we set up some requirements for the solution we were going to develop. So firstly, the geometry needs to be able to move dynamically. You need to be able to open doors, and that changes how the reverb, the propagation, the occlusion of the whole scene sounds. It needs to be high quality. We know sound designers have very particular tastes. They're not going to settle for a compromise on quality to get a little bit of accuracy. We need to be maintaining a really high quality bar for the audio. And we need to give them control over how it sounds. We need to give them the right knobs and dials so they can dial it in to sound how they want the space to sound and give them control. And you have to be able to play a lot of sounds. It's computationally complex, but people aren't going to settle for just having half a dozen sounds. You still need to be able to play 64 sounds or more in your scene at the same time. And so Facebook Reality Labs took these pretty difficult constraints that we put on them and worked on the problem, and they came up with something really special. I've got a demo of what they put together right here. So this scene, you can see it's a concrete space. It's open at the top, and there's 21 sources playing simultaneously in this. They're all stems of a different song, and they're all moving around dynamically. And throughout the video, the geometry of the space also changes. So I'll play that for you now. And you can hear how the space opens up as that wall disappears off into the distance. the reverb gets bigger, and the whole space sounds like you're in that space. And this is really, really amazing. When you're in there and you hear it, it really reinforces the visuals, and you really get to appreciate how important getting the reverb correct is. And so we've taken the technology they've developed, and we're working on integrating it into the Audio SDK right now. We've got a little progress video to show you. This is far from final, but this is that same system in Oculus Home. And excuse the mess. And so this is a really interesting environment to model because it's not entirely an indoor environment because it's got that large open wall, but it's not exactly an outdoor environment either. So trying to do the reverb for this correctly with impulse responses or a parametric reverb will be very difficult. And it's highly asymmetric, that you've got this big wall behind you. And so modeling that correctly with existing technology would be very, very difficult, if possibly impossible. So we really thought this was a great place to dog food this tech. And dog fooding this tech was really important for us because we wanted to make sure that what we were delivering to you would meet the Tom's high quality standards, as well as the performance targets of hitting frame rate and all of that, and not compromising in any way.
Yeah, one thing Pete's not telling you is that how fantastic this sounds in headphones. It's hard to tell here through speakers, just how spatialized everything is. So when you're standing in this room, if you've been at home before, you know, like right there, we're standing back against the wall. As things are bouncing around the room, you hear the things slap back off the wall behind you. It sounds kind of odd in here, but when it's in the headphones, everything sounds like it's right. You hear the slap back behind you. You hear all the long trails like off in front of you, just like the reverb fills more in front of you. As you turn to the left, then you still hear the wall. Like you will know when you're next to a wall without even seeing anything. You can feel everything. It's amazing. This video, Pete was just up in Seattle from Australia last week, and he was over at Facebook Reality Labs where they've been working on this. He brought the video back. As like, that has to go in the talk. As soon as I heard it, I sat there and listened to it like over and over again in the studio, just trying to get like, oh, this is fantastic. And like, I've just seen the video. I know it needs some more work before it goes in, but I'm super enthused and happy about where they're at right now.
Yeah, and this is really interesting. And I think one thing we've learned from all of this is how it changes how we deal with reverb. Reverb itself is been worked on for a very long time. We've come a long way with reverb technology, and making a pleasing sounding reverb is relatively straightforward, and it's a well-explored area. But making an accurate reverb is completely new territory. And trying to get an accurate reverb that's also pleasing is a whole new challenge.
So this is weird now. This is another one of those times that sound designers are going to be like, what are you doing? This is backwards. And like Pete was saying, people make lush, gorgeous sounding reverbs. This reverb is realistic. It sounds like the room you're in. In Unreal, you go in and you tag the surface types for each wall. That's all you do. It does the reverb by itself. But that means if a designer builds a square room that sounds bad because it's going to have standing waves and everything's going back and forth, guess what? Reverb's going to sound horrible. It's going to sound like the real room. So you have to work to tweak this to make it sound good. Sometimes you may want the horrible sounding realistic reverb. Let's say like you're in a jail cell and you have things flapping around with like concrete walls. It's going to sound bad. It's going to sound just like that room sounds. We're like working to get like mix volume in there. So like how much reverb are we going to have in there? Like we can turn it to make it fully realistic. So if you're doing AR stuff where it's everything has to be super realistic to fit in the actual room you're in, that's good. But sometimes when we're making different spaces, we want things to sound nice all the time. So we'll have mix. And another thing you can do is change the different surface types of the walls. So if they're brick walls, maybe go to a plaster wall or whatever else. I think there's 20-some different surfaces to choose from right now.
There's a whole bunch, yeah.
Yeah. So you're going to have to work backwards compared to what you're used to working in. And I know it's unintuitive, but the power of this is so good. It's amazing having it sound this good. In the video, there was a point where he threw a basketball, it bounced off a wall, hits a couch, and then goes outside. And the coolest thing about that was like, as it goes outside, you hear it slapping back behind you again. but then the time delay as it moves farther away from you is just slight, but it's very realistic. And it sounds like we're always trying to sell that immersion feeling like you're in a room, and that's what this does. This opens up some problems. So if you're working with a level designer and they build that square room, you're gonna be like, hey, this sounds bad. And they're gonna I don't care. They're just not gonna care. You're gonna work with them, and if you can, this is gonna be the easiest solution, is catch them early. Audio always needs to be in early. Work with them. Can we just make this more of a rectangular shaped room? Just a little or something? Can we do something? They're gonna laugh at you, but you can try. This is the look I got from our lead designer. That's Richard up in the Oculus Rex team. Dude, no square rooms. He's like, no, I'm not an acoustician. I'm a level designer. I've got to make this game fun. I don't care what the room type is. So, spatialize everything. I keep saying this every year. I've been talking to people, and I'm hearing these games, and I get disappointed sometimes. And people are like, I put your spatializer on one or two things. And I'm like, no, it's not a gimmick. It's not a toy. This is kind of your new world now. Take advantage of this technology. It's amazing, and you want to make everything feel like it's coming from some space around you. You want to feel like you're in that space. Whenever I hear anything that's not spatialized, that means it's also not externalized. That means it's just in my ear. There's nothing natural except having headphones on that sounds that way. So there can be reasons to do it. Like everything, there's always times to break the rules, but spatializing everything is so important to make everything feel realistic. Reach out to us if you're having any problems. Pete and I are always around. The Oculus forums are a great place. There's a whole audio section there. I know Pete gets his phone ring all times of the night in Australia because people are like, hey, I want to do this thing or whatever. But we're here for you. We're trying to make the tools better for everybody to use. We've been doing this for 4 years now. The tools have consistently been getting better and better and better. There's new tech, like the propagation tech, I'm so excited about. It seems like it's just going to make my life easier or harder. I don't know yet. We'll find out. And then explore, try out new things. We want to, it's still early, right? Everybody who's working in this space knows that it's still early, and new tools are always coming online. So just explore, have fun. Reach out to us, let us know what we can do to help, and just that's about it. And we're going to have questions now.